So in this question, it's a pure data analysis question. We have a situation where we have these two ladies who have mixed varying degrees of paint, black and white paint, to produce different shades of gray, and they want to see what effect it has when they're putting it under a heat lamp. And so the truth about a question like this is we don't really need to know much about the situation to answer all the questions that are asked of us. It's really about the process of breaking down and analyzing a graph. So, of course, we see there's a graph here, and we're going to start right off with our Oizerga. And so we see we do have a 0, 0 origin. Our y-axis is temperature in degrees Celsius, and the scale, we can see it goes by ones. The x-axis is B, which is the percent of black paint in the mixture. And let's see, that's 10, so we see in this case it goes by 2. So each increment there is by 2. And that's B, that's a percent, and it goes by 2. And we notice now we have some error bars. It tells us that the uncertainty in the B is so small you can't detect it. But in the temperature, we can see it's plus, and we look at more than 1 point, we can see that it's plus or minus 1. So we'll write that down right off the bat, plus or minus 1 degree Celsius. All right, so that's our x-axis. We look at our intercepts. There are no discernible there are none, not an x nor a y. Excuse me, there is a y when we draw it, but it's not going to be 0. So there will be some kind of intercept over here. That will come about when we draw a best fit curve through the points, like so. Let's finish that off there. And we drew these best fit lines. We needed to kind of make sure it's pretty smooth. Well, we can read temperature and B. The gradient is delta T over delta B. And that is going to be the degrees Celsius per percent increase in black paint. The area is degrees Celsius times percent. And percent isn't really a unit. It's a ratio. And so if we said we had 5 of the beans in a bag of 15, 5 beans out of 15 beans in a bag, beans in the bag, well, we see that's 1/3 or 33%. But it's a percent, but beans cancel. There's no real units on it. So percent is not a real unit in and of itself. So there's nothing that jumps out as any kind of physics quantity, and we wouldn't expect it to, given the scenario here, since it's not about our typical physics content. It's about our physical content. So now it wants the first question after we've done our Oizerga is state the value in the absolute uncertainty in T. We've actually already done that. And so the absolute uncertainty in T is plus or minus 1 degree Celsius. So that's easy. We've already answered that part of the question. Moving on to the second part. Comment on the fractional uncertainty. And the fractional uncertainty is what we think of as the percent uncertainty for the measurement at B, a 10, and B of 90. So that's like a U percent is the absolute over the value, and we'll do that twice, is the absolute over the value. And so for a value of 10, what we're talking about here is how does this uncertainty compare to this uncertainty? Well, we can see the uncertainties are the same size and B is bigger. So we should expect that standard thing that the uncertainty decreases related to the size of the measurement as it gets larger. So we should be able to see that right off the bat, but we can calculate that. So at 10, we've got 10 and the value is it's 14 plus or minus 1. And this value up here is 33 plus or minus 1. So we have 1 out of 14 and we have 1 out of 33. And so what we can comment on then is to say that as B increases, the fractional or percent uncertainty decreases We could go further to say because the absolute uncertainty remains the same, and B, and we could even say denominator, increases. So we've figured out and commented on that. And now we're asked to draw the best fit line, which we've already done. And now we need to outline why the data don't support the hypothesis that T is proportional to B. And so our justification here, we need to start with a physics principle. Well, what does it mean for something to be proportional to B? To be proportional to B, or we could say for T to be proportional to B, T to be proportional to B, the data must be a straight line, and what makes a line straight is constant slope. You know me, I like these parenthetical expressions that are more specific about the graph. It must be a straight line, in other words, constant slope, and pass through the origin. So that's the principle. That's the criterion by which we would judge this. This is the physics principle, the principle. The data is not a straight line because a straight line cannot be drawn through all the error bars. So again, looking at that graph, if we tried to draw a best fit line, we put a straight edge on there. There is no way to put a straight edge on there and get that line to be straight and pass through all of those error bars. So we can get a bunch of them, but if you look, even in this case now where I've got the green line, I can only get it to pass through 2. If I wiggle it, I might be able to get 3, but there's no way to do this because the data isn't in a straight line. It's not increasing at a constant rate, a constant slope. So the data is not a straight line because a straight line cannot be drawn through all the error bars. Moreover, the best fit line does not pass through the origin. So T is not proportional to B because it is not a straight, the data is not a straight line and it does not pass through the origin. And so now we move on to part B. We have this question here, we're given a function. So whenever we're given a function like that, the first thing we should try to do is see if we can make it a line. So we rewrite the equation down below. We write that equation down below, which is T equals KB to the 1/2 plus C. And we want to know if that's a line, so y equals mx plus b. So we can see C is the y-intercept. The y-axis should be T. The x-axis should be b to the 1/2, and the slope is k. So if we have a graph that is this, the square root of b to the 1/2 against t, if this is the true relationship, it would produce a straight line. So to test whether this is true, they actually transformed the data, and they plotted the data on the graph. And so we should do yet again another Oizerga on this graph. We have an origin of 0. The y-axis is still t. It is still t. X-axis is now the square root of b, or b to the 1/2. The intercepts, there is a y-intercept, and that y-intercept, if we look closely here, we can see that's 4, that's 5. It's maybe a little bit more than halfway, so we might say the y-intercept is 4.6. The things we can read from the graph are t and the square root of b. The slope is delta t over delta square root of b. Not a known quantity, but that's what it's equal to. And the area is delta t times the square root of b. So that's what those quantities would give us, whether or not they have meaning. So we've broken this graph down now. We see there is a straight line. We check the uncertainty, and the uncertainty is, again, plus or minus 1 degree Celsius, which makes sense because y wasn't transformed. The uncertainty would stay the same. This goes by ones. And the horizontal axis, let's see, that's 1, and we have 5 increments, so it goes by 0.2. Goes by 0.2. So now we're ready to answer some additional questions. Use the graph to determine the value of C with its uncertainty. So we want to say explicitly that C is the y-intercept and is 4.6 degrees Celsius. Now, so we've said the value of C, but now we want the uncertainty. The uncertainty, we know the absolute uncertainty, is always the upper limit minus the lower limit over 2. So if this is our, it's the plus or minus, we have our mean value, we have our upper limit and our lower limit, and the mean should be situated right between the two. Well, so the question then becomes, how do we determine an upper or lower limit of the y-intercept? Do we just use the size of the error bars, or do we do something different? And the answer is we do something different. What we do is we draw 2 lines, the steepest possible line and the shallowest possible line. So we can take our line, and we'll try to do is something like the rightmost point near the upper end of the error bar and near the lower end of the error bar on the farthest one. And then we do, that will give us the steepest slope we could possibly draw. And now we want to draw the shallowest slope. And we adjust that like so. And of course, I didn't do a very good job. But what this does then is allows us to come up with an upper limit, a lower limit, and like an average value, like so. Now, these are extreme. They're larger than they should be. But we can see then if we've got a mean of 4.6, this is certainly going to go up to, this one needs to come down. So maybe like this. So maybe it's 7 is the upper limit, and maybe the lower limit, let's say it's 2. So we go 4.6, 7, and 2. Well, we can take that back to our other work page here, and our upper limit is, say, 7, and our lower limit is 2. So that is 5 over 2, or 2.5. So that's 4.6 plus 2.5 is 7.1. Minus 2.5 is 2.1, like so. So we might say now that we've got this uncertainty of plus or minus 2.5. So, and looking from the starting with the leftmost decimal place, we don't agree with the ones place. So let's round these numbers off, and this would give us 7, and this would give us 5, and this would give us 2. And so now if we use the upper limit minus lower limit over 2, we get 7 minus 2 over 2, which is, again, still our 5 over 2, or 2.5. So what we are going to say then is our mean value is 5 plus or minus, depending on what our numbers were, either 2 or 3. So in this case, I'm going to say that the absolute value is 5 plus or minus 2 degrees Celsius. And that's how we would approach that. There's sort of, it's not exactly like purely scientific, but we certainly wouldn't say plus or minus 1 on that, because given the lines we've drawn, there is a greater uncertainty in the y-intercept than just plus or minus 1. But it's not as large as 3, so 2 is a better answer in that case. Now we want to know the constant, state the unit of k. And looking back at our equation, we said k is the slope. And so the slope is delta y over delta x. And the slope has units of degrees Celsius, and x has units of percent. And we said previously, percent is not really a unit. So the units of slope are degrees Celsius. And so degrees Celsius. And since it's saying state, we don't have to show how we got it. We can just say degrees Celsius. And so that's how we do question A2.